Hello everyone, so welcome back to my channel. So now it's time to do the third question of Leetcode weekly challenge. So basically this question, when I first encountered, then I thought that this question is somehow similar question which I had done before. Actually this is the question similar to that burn leaf question. Means but that burn leaf question was like that we were burning the leaf from one leaf node, and then how much time it will take to burn all the leaves. But somehow it is similar to that, but somehow it is also similar to one more question which is being there for doing multi-source DFS. That is that rotten oranges question, in which we are starting from one point and all the oranges which would be just surrounded by that particular orange, that would be rotten at that particular minute. So this is somehow similar to that question also. So just a combination of two questions, but it is more preferred towards that rotten orange question. So that's why in this particular tree which is being given to us, we will convert this tree into a graph. And after this particular is converted into a graph, then it becomes a question of that rotten oranges question only. So basically, first point here would be that we would be converting this question into a graph, and then after converting this question to the graph, we would be then directly traversing it, that whatever are the adjacent nodes at that particular point of time, at that particular point of time they would be turned into the infectious nodes, and then after that at the next minute we will check that what are the next nodes which are being there, which are required to be infected, and then after that the other next nodes. Basically when we are, 1 minute, let me turn it on, actually it got off. So basically what I'm saying is that at 1 minute when we are at this particular moment, then the node which is surrounded are these two, right? So when it would be a graph, then these three nodes would be adjacent to this, right? So that's why at this moment means at the one itself we would be getting these two. Means these three nodes are infected. Means when it comes out to be 2, here if we take at 0, and then at the 1 minute, when it happens the 1 minute, then these nodes would get infected. Then after that, here there is no node, means there is no node here and there is no node here, right? But there is one node here. So at the 2 minute this will get infected, at the 3 minute this will get infected, at the 4 minute this will get infected, right? So like this, at the end we are getting the answer as 4. So this is a thing which we are required to do in this particular question. But yeah, I just directly explained you the question because when I saw this diagram and read that and somehow just came to the question, then I just thought that yeah, this is similar to that question. So let me first go through from the question. You are given root of a binary tree with unique values and integer start. At minute 0, an infection starts from node with the value start. So this is thing which is being given to us. All the values are unique, no duplication is there, and there is one start node which is being given to us, from where the infection starts. And each minute a node becomes infected if the node is currently uninfected and the node is adjacent to an infected node. So the thing is that node is currently uninfected, then only it will get infected, else it is already infected, so it won't be counted into our answer. But there would be only one node given to us which is infectious, so and that would be the start node, and the node adjacent to the infected node will become the infected node. So basically by this first line they wanted to say that when in this we were there, right? So in these, all these became infected. So now when all these became infected, then at the next minute we are not affecting any of these, but these will affect the other adjacent nodes. So that's the thing which they wanted to convey. And at the end we are required to return the minimum number of, not the minimum number, but the number of minutes, because there is no minimum in this, no maximum in this. We are just going ahead with the flow, that what are the next nodes which are there coming up, and then they will get infected. So that's the thing which we are doing here. So in the first example, I already explained you that how they were getting infected, means all the adjacent one got infected. But if you think, if we do any sort of DFS in the same or DFS in the same on the tree, right? So would we able to come up with a solution? Because when we do DFS or BFS on a tree, so it is in just one direction, and then in the backtracking part in the DFS portion, it comes back to from where it got started. But here the node is also different, means a root. You can better say that the starting node where the infection is starting, that is here acting as a root node from where we are required to start for a traversal of the tree. So that's why it would be better to convert this particular tree into a graph. In actual, a tree is already a graph only, but the graph has some more properties than tree, but still means the tree is, you can see the sub part of a graph. So that's why we can easily convert this tree into a graph after creating the undirected edges in the same, or even the directed edges in the same. But the thing is, why we are creating an undirected graph in the same? Because we don't, because we require to move from parent to child and child to parent. Both would be the same case, because you can see in this 3, we are moving to the parent, moving to the child, right? And this is also the child. And also we are moving to the parent, that is 1, right? So in that context only, we are required to make an undirected graph. So that would be our first part, making our undirected graph. And then after making the graph, we are required to traverse into this graph from the starting point, that is from the 3, which is being given in our present example, right? So first point would be making the graph, and the other point would be traversing the same. So that traversal is our choice, that either we want to do a BFS traversal or DFS traversal. That's completely our choice. But here the thing is that BFS, DFS both will work in the same. So that's why presently I'm just going ahead with the BFS type of this particular. So I'll show you the BFS code. So let's go ahead and start with the BFS code here. So in this, first I will show you the constraints which are there, because it is a tree given to us, right? And even when we are making the graph, so the constraints are in such a manner that it won't give us any sort of TLE, because in the graph also we are traversing all 10 to the power 5. Order of anything would be there, or at max it would be E plus D because of the adjacency list, right? And even the space complexity, that would also be E plus D, that is the number of edges which are there and the nodes which are there. So that's why it will already be bounded inside these constraints only, no TLE would be there. And the node value, because we are not adding up them, right? So here we are not concerned with the node value, and even we are not concerned with whether it is negative or positive. So now let us go ahead with making of this particular graph. So here the traversal I'm doing, and here I'm making of this particular graph. So now for this particular graph, I'm taking an unordered map for our adjacency list, so that we could easily look up in the same. We could have also used a vector of vector, that would also have worked, but here taking unordered map make it easy for lookup and so on. So that's why I've taken that. So here in the first, the value of that particular node would be stored, and the corresponding edges which are being connected to the same, that would be stored in this vector of int. So that's what I'm taking here. And now creating this graph. But before creating the graph, let me show you that how we are going ahead. So here we are directly calling our create graph function. So here our graph would be created and then returned. And when it gets returned, then we would be doing the BFS on this particular for calculating our time. That's the thing which we would be doing here. So now let me show you that how we are creating this graph. So here we are basically creating an undirected graph by using the BFS method of creating the graph. So what we are doing is, here we have taken a queue, and queue is also in the pair form, pair type. So first we are having that particular tree node and corresponding to its value, that we are having here. So at the first time we will be pushing that root, the first node which is there, and its corresponding value we are taking the -1. Basically here it basically stands for the means what is the parent value for the thing, and the root won't be having any parent, right? Because root itself is a parent. And then we would be going ahead for making our graph. So here, and this is for this whole, means this particular, this whole while loop, that now we are having something in our queue, right? So then first thing which we would be doing is, we will be checking node and the parent from this particular queue, right? So root node will be checked out, and it will be popped out from the queue, and then we will check. The parent is basically stored into this particular portion, that is this -1. So we will check that if it is not -1. At the root point, it would be -1 only, because root don't have any parent, right? So if that is the criteria, then we won't be going into this particular loop for making our graph, but we would be going in this because it is a tree. So surely that parent would be having left child and right child, right? So that's why we would be checking for this particular node's left child and right child, and then we will be pushing those left child and right child as it is, and the node value, and the node value is basically here the value of the root which is there, and that is the parent of this left and the right child, right? So that's why we will be pushing that into the same. And then we now our queue is still not empty, right? So that's why again we will be going ahead, and in the now we will be setting out our second node which is there. Earlier it was root, now our left child would be at the first, and that we will be fetching out, and for the left child we will be getting a root as the parent. So that's why here we will be entering this condition, because their value won't be -1, it would be something, right? And here even this -1 from that particular constraint also, if that the other constraint were not given as that the value of the node are all positive, then surely here for this particular what we say for this root, rather than taking as -1, we would have been required to take int max. That would be the same here. So that's why that particular is helping us out, means those constraints are helping us out. So here you can check that if there is a parent, right, because left would be having a parent as root. So in that criteria, we will be directly pushing that node value which is there, means the left value, to the adjacency list of parent. That is, root is being connected to our left. That we would be doing. And the node value, by taking the node's value, we will be pushing the parent value to the adjacency list of the node value. And why we are doing so? Because here we are creating undirected graph. So that's why we are pushing parent to the node and node to the parent. Both of the things we are doing here. So that's the thing which we are doing here. So this was the part for creating a graph, and this whole process would go on, and the graph would be created completely, an undirected graph. Now after the graph is being constructed, now comes the part of taking out the time of from that particular graph, and how we are doing that. So here I am taking the method BFS rather than doing DSS. That also we can do, but generally BFS. So here what we are doing for BFS, we require queue as the way we were requiring in that making of graph also. So here also we are requiring a queue, in that we are pushing our values, and then unordered map. Why we are taking this unordered map is for the fact that if we have already seen that particular node earlier, then that would be marked as true or false if that has been seen. So from there only we would be able to check that was it already infected or not. So that's why we are taking this particular. Now we will be pushing our start node into our queue. Why we are pushing our start node, not our root node? Just because of the fact, because we are required to start our BFS from our start node. So that's why we are pushing our start node to our queue. That is the thing which we are doing here. And then we will be marking that start node as seen equals to true, just because of this fact. And we are marking it as true. And then after that, in time equals to 0, because at the starting our time is 0. And then we are going ahead till the size of the queue. And then here we are basically checking for our time, that basically increasing our time. Rather than taking this for loop, we would have been increasing this time here also, means in this while loop, because at each time it would be increased only when a particular level is completely traversed. So that's why we could have also taken that time at this particular position also, then also it would have been worked, but we are taking it here. That would also work, means the two methods of doing the same thing. And then we are taking the size of the queue, that what is the present size of the queue, and according to that size we would be running this loop for checking the same level of all the queue which are there. And then here we are checking for node equals to queue.front and queue.pop. Basically we are checking for the first node. And then after that what we are doing is we are checking that for I in that particular V of node, means the whole adjacency list of that particular node, that we are checking, because at this moment after this, means whatever node is being there, we will be marking them as seen, pushing that particular to the queue, so that other nodes which are being attached to that particular node, they could also get infected. and then we will be marking that as that it is now already being listed and being infected. So that's the thing which we are doing in this. And after this, all the nodes which are being attached to this node, they would be completely infected now. And then we would be going ahead with the other nodes which are being there in this particular queue. And this is all which we will be doing all in the repetition form, and thus we will be able to count the time. And then at the end, after exiting from that loop, we will be returning time minus 1. Why we are doing so and not returning direct time? Just because of the fact, because we are not counting the starting node's time. You can clearly see in this particular example that the node's time was starting from the 0, right? And the all other time which was there, that was being counted. But here, when we would be doing this particular thing, means this time plus plus from the starting, also it is counting for the root time also. So that's why at the end we are returning time minus 1. So this was all for this particular question. So time complexity and the space complexity for the question is order of E plus V, and same for the phase complexity because of making up this graph and even traversing in this graph and then storing the same. And yeah, this was all for this particular question. If there's any doubt, you would comment that down. And yeah, this was all.